Happy to be here and share with you my research work during my master degree. My name is Longyue Wang, majoring in software engineering. My supervisors are Professor Zhou and Professor Huang. Today, the topic of my presentation is domain adaptation for statistical machine translation. Let's first have a look where we are. This tree shows our research scope. We mainly focus on domain adaptation approaches for domain-specific statistical machine translation. My presentation today will follow this agenda. Firstly, I will give a brief introduction, including the background and problems, and then I will go straight to our three proposed methods and its experiments. In part 5, I will show you how to apply the domain adaptation approaches to a real-life system. And finally, I will give a short conclusion. In this part, I will follow three questions. The first question is, what is statistical machine translation? SMT translations are generated on the basis of statistical models whose parameters are derived from the analysis of corpora. Currently, the most successful approach of SMT is phrase-based one. So I saw this framework to show you how does it work. Firstly, models learn from the corpora, the collection of text. For example, each English sentence is paired with its Chinese one. We call it pairal corpora. If we only consider one side, we can call it monolingual corpora. From the pairal corpora, we can get the word alignment information using the EM algorithm, and then extract the phrase pairs for translation table and reorder table. From the monolingual corpus, we can build the language model, which assigns a probability to a sequence of words. After the training part, all the models are generated. So I will apply this decoding function to retrieve the best translation candidate. It can be split into three components. The first is phrase translation table, which ensures the foreign phrase to match the target one. The second is reordering model, which reorders the phrase appropriately. And the last one is language model, which assures the output to be frequent. So my second question is, what is domain-specific SMT system? Let's firstly have a look at the typical one. It is trained on large and broad corpus, which we often call it general domain corpus. And it deals with the text, but often ignores the domain problems. Here are two real-life systems. For example, the Google Translate and Bing Translator. Their performance depends heavily upon the quality and quantity of the training data. For example, if I give Google Translate a BBC News, and we can get its Chinese translation. As a native speaker, we all know this sentence is wrong, especially in its structure. However, we still know its general meanings. So I call it understandable translation quality. Now you will ask, is this translation good enough? Of course not. So people proposed the domain-specific SMT systems. It is trained on a small but relative corpus, which we often call it in-domain corpus. It deals with the text, maybe from one specific domain. But we have to consider about the training data and what you want to translate. Here are two real-life systems. The iconic translator is mainly focused on the patent domain text translation. So I give it a Chinese patent sentence and get its output. I will say the English translation is perfect because it not preserves the semantics of the source side, but also keeps the morphological and syntactic practice. I call it publishable translation quality. So my third question is, to achieve this perfect translation, what is the challenge? The first challenge, I call it ambiguity, because multi-meaning may not coincide in bilingual environment. For example, the English word mouth can refer to meanings, an animal or an electronic device. However, in its Chinese side, it can refer to 3 different Chinese words. During translation, it may generate several translation candidates, but different systems may prefer different one because they are built based on different knowledge. The second challenge, I call it Longyue style. By observing this news domain text, we know it tries to deliver the rich information with very economical language. The sentence is short and a simple structure can make every of us to understand. But it has a lot of abbreviations, date, and name entities. However, the legal document is totally different. It is very rigid, even with duplicate terms. It uses fewer pronouns or abbreviations to avoid any ambiguity. And also, the high-frequency words are shall, may, or must. On the whole, the sentence is very long with long subordinate clause. Now we know sentences from different domains may have different language style. The third challenge, I call it out of vocabulary. Words or phrases occurring in specific contexts may have specific meanings. We call it terminology. However, the terminology may have many variants or combinations and may increase every day. So, a dictionary cannot capture everything. For example, in this Oxford English to Chinese dictionary, there is only a very small piece of data or terminologies. So, during translation, if the input terminology does not learned by our model, we will never know what does it mean. Until now, we know SMT is corpus-driven, but there may be a mismatch between the domain of available training data and the target domain. What is worse? The training resources in specific domain are usually relatively scarce. So, in such scenarios, various domain adaptation technologies are proposed by leveraging the general domain data. Domain adaptation can be employed in different SMT components. For example, the word alignment model, the language model, the translation model, or real-time model. And also, various resources can be used for domain adaptation. For example, the monolingual, apparel, or comparable corpora, or even the dictionary. If we consider about the supervision, we can also use the semi-supervised, supervised, or unsupervised method to do this task. In my thesis, I explore the data selection to solve the ambiguity and language style problems by moving the data distribution of training corpus to the target domain. I also explore domain-focused web plugin to reduce the OV problems by mining some useful data from the web site. In this presentation, I will mainly talk about data selection. What is the definition? We have a very large and broad general domain corpus. The sentence in this corpus may come from different domains, for example, the law, the subtitle, or news, or novel. But we only want to translate the spoken domain text. So instead of using the whole data, we only want to select a small piece of the relative data to train our SMT system and do this task. This is my translation model adaptation framework. We have 2 kinds of corpora: small in-domain corpus and a large general domain corpus. I apply a store function to measure their relevance and rank the sentence in general domain data. And then I will select the top key % of general domain data as the procedural in-domain data. Now we can use them to build different translation models. If you want to further improve the performance, you can also use the log linear or linear interpolation to combine them. The language model adaptation framework is similar. The only difference is we consider about the target site language information and build language models. After adapting these models, I will use it to translate the input sentences maybe from one specific domain, and I will evaluate their output to show their performance. There are already some work. The first famous model is vector space model. It converts the sentences into a term-weighted vector and apply them to a vector similarity function to measure their domain relevance. And another famous one is perplexity-based model. It employs the n-gram in-domain language models to score the perplexity of each sentence in the general domain corpus. They are based on cross-entropy and perplexity. Both of them are monotonically related, so we can use either of them to do this task. Until now, there are already 3 perplexity-based variants. The first is cross-entropy, which only considers the inside source language information. More devices began to try to select the sentence that are more similar to the in-domain but different to the out-of-domain data. Based on them too, modified derivatives began to consider both the source and target language information. By reviewing their work, I found that the VSM-based method can obtain about 1 blue score improvement using 6% of the entire data. But perplexity-based approaches can do better. It can allow to discard 50 to 99% of general domain data, result in an increase of 1 to 1.8 blue scores. You will ask why they have different performance. I think VSM-based similarity is a simple concurrency-based matching which only weights the single overlapping words. But the perplexity-based similarity can consider more. Not only the distribution of terms, but also the n-gram word quotation. So I set them in different grade level in this figure. Now I wonder if there is a higher grade level similarity function to achieve a better performance. Finally, I found the string difference similarity function can comprehensively consider the word overlap, n-gram quotation, and word position. So my first proposed method is edit distance as the new data selection criteria for SMT domain adaptation. Given a sentence SG from the general domain corpus and a sentence SI from the in-domain corpus, I apply this normalized edit distance function to measure their similarity. In practice, for each sentence in general domain corpus, I transverse all the sentences in general domain corpus to calculate their FM scores and average them. To conduct our experiment, I use a large and broad general domain corpus, which includes the 5 million sentence pairs. For the in-domain pair corpus, I use RWSLT dialog task data, which is traveling domain. And I built several systems. The baseline system is built on the entire general domain corpus, and the VSM-based, perplexity-based, and our proposed method are trained on the top key percent of the entire general domain data ranked by corresponding method. We set our key at 20, 40, 60, and 80. Here is our result. You will see the 3 adaptation methods can do better than the baseline, and the VSM can improve nearly 1 blue score using 80% of the entire data. Perplexity-based method is really a simple but effective method because it can increase 1.1 blue score using only 6% of data. However, our proposed method can do best. It achieves the highest blue score with less data. Now we can draw some conclusion. Our proposed method is better than cross-entropy, and then the percent TF-IDF, and then the baseline system. As you see, the high grant similarity function can perform better than the lower bands. But different grade level methods may have their own advanced nature. So I think, how about combining the individual models together? Now, the second proposed method is a hybrid data selection model for SMT domain adaptation. We investigate the combination at two levels. The first is corpus level. Now, we have several genome domain corpus ranked by different similarity function. I transverse all of them one by one to our combined corpus. And if I think one model is more important, I can increase the synthesis concurrency times with them. And the model level combination is similar. The only difference is we didn't combine the transverse synthesis together, but keep them in original state, train a translation model, and finally I will perform a linear interpolation on all of them. For the corpus, I still use large and broad genome domain corpus. And the in-domain corpus, I use the LDC data, which is the Hong Kong law domain. And here is our corporal statistics. Now I built more systems. The base one system is same, still trained on the entire genome domain corpus. For the individual models, I also explore all the complexity-based variants, cross-entropy, Marley-based, and modified Marley-based. The combined model, I explore the corpus level and model level combination. I set my key like this. And let's firstly have a look at the individual model result. The red data show that the complexity-based variants are all effective. And the modified Marley-based perform best. It can improve the nearly 2 blue score with only 15% of the entire data. Now we can see the modified Marley-based is better than our proposed one, and better than the cross-entropy, and then the Marley-based, and then the cos-NTF IDF, and better than the baseline system. I draw the data in this figure and found that the good performance always happens between the 7.5 and 30%. So I will further conduct the combination method in this section. Considering the different nature of them, I will further combine the modified Marley-based and the cos-NTF IDF and our proposed one. This is a combination model result. Obviously, the two combination methods perform better than the best individual model, slightly. And the model level is a little bit better than the corpus level. And we can conclude that the combined models are better than the individual models and better than the baseline. Until now, I have explored many data selection methods, but I found all of them only consider the word itself. I think it may result different problems. For example, the sparsity problem, or it is weak at capturing the language style, the sentence structure, or semantic information. So I proposed my third method, the linguistically augmented data selection for SMT domain adaptation. We explore the two combinations in this method. I still consider about the surface information because it has very rich lexical information. And I also explore two more linguistic information. So the first is named entity categories. It groups together the pronouns that belong to the same semantic class. And the second one is part of speech. It groups together the words that share the same grammatical functions. In practice, I firstly changed the original corpus into different linguistic formats and use them for language model training and synthesis scoring. Then my co-metric similarity function is modified multi-ways because it is the best individual model for data selection. And finally, according to their scores, I will select the data from the original corpus to train adapted SMT models. Based on the individual models, I further combine the different type of linguistic knowledge at corpus level and model level. The methods are same as our second experiment, so I will not talk about it again here. And for the experiment, now I use a very large general domain corpus. It has 10 million sentence pairs. For the in-domain corpus, now I use RWSLT TT-doc data, which is talk domain. Here, the system is a little different because all the adapted systems are not linearly integrated with the in-domain model to further improve their performance. So the baseline now is trained on all in-domain plus general domain data. For individual model, I explore the service form-based, POS-based, service plus name entity-based, and the service plus POS-based. Combined models are corpus level and model level combination. I set our K at 25, 50, and 75. Here is our individual model result. The red data show that after adding more linguistic information, Fn and Ft can improve the baseline about 1 blue spot. But if we only consider the POS information, it will perform poorly because this will leak off reads the lexical information. And if we consider the Fn and Ft to outperform the baseline, so I will combine the Fn and Ft for the combination experiment. Here is the combination model result. I will say both combination methods can do better than the best individual one, about 0.64 and 0.11 blue scores. I think combination may success the advantage of its linguistic-based method. And I guess if this method applied to highly inflected language pairs, such as English to German, it will get a better performance. Because for these language pairs, we can use more useful linguistic information. For example, the steamer, the lemur, and so on. The part 3 is our real-life system. WMT is the most famous workshop with high-quality shared tasks on machine translation. We attended it this year for medical translation tasks. So we have 6 language pairs and very large resources. For example, the general domain parallel corpus, it can up to 36 million sentence pairs. And also, the medical texts are very complex. For example, it has so many chemical formulas. Finally, for this task, we presented a number of detailed domain adaptation technologies and approaches. For example, the task-oriented pre-processing, the language model and the translation model adaptation, and the numeric hyphen-word adaptation, and combine all of them together to our final model. Finally, we are very happy to see we got the first rank on 3 language pairs and the second rank on others. As we outperform the other universities, such as Edinburgh or DCU. Based on these models, I also developed my first online translator, Bentu, which is a domain-specific multi-tier SMT systems. This is a framework of a Bentu system. It has 3 framework, 3 layers: pre-processing, decoder, and post-processing. I think this framework is perfect because it is easy to add any new language pairs, domains, or AMP toolkit. I want to say thanks to my colleague Anson and my other colleagues in Iconic company. Under their help, I can build my first SMT system. This is the user interface of Bento system. I do believe after training all the models, we will publish it. And finally, I will give a conclusion. Actually, I do more work out of today's presentation. For example, for the domain-focused web plugin, I also proposed the integrated model to improve the performance of cross-language document alignment. And I also combine the topic classifier and the complexity model to filter the clouded noise data. I also do more work out of my thesis. I draw this tree to show you all my work on natural language processing and machine learning in the past 3 years. My work is still ongoing. I still want to explore the new models for data selection. For example, the graphical model and the neural language model. For the domain-focused web plugin, I want to explore how to manage the more useful and the accuracy in domain dictionary. For my real-life system, I want to extend more language pairs and domains, and then finally publish it. This is my publications in the past 3 years. I have 3 journal papers. 2 of them are SI journal, and I have 11 conference papers, and all of them are ER index and ACL authority. And finally, I want to say thanks to all of you. Because of you, I can work to here from my hometown, my small hometown. So I think all of you are my best gift in my life. Thank you.